So, good morning. It's a pleasure to be here to present the results of our work on wireless telemetry platform for energy harvested in tires, which was done by a group at Università of Bologna, together with colleagues at Nokian Tyres. So, we will have a first introduction about smart tires and how to power them. Then we'll describe the structure of the design and the wireless telemetry system, and with the focus also on experimental results we have obtained. So tires are an important part in vehicles. They are strictly related to safety, energy efficiency, and basic monitoring systems are now a reality, like TPMS, for example. But now a new category of sensor is emerging, so-called smart tires. They're devices with enhanced multiple sensing capabilities, enhanced connectivity, and local computation capability at the edge, for example, which allow cloud applications and applications like fleet management and similar. As an example, our colleagues at Nokian Tyres are developing these small devices, and they are placed inside the tires. They can detect multiple quantities like pressure, temperature. They also have other types of sensors. And they allow wireless connections with application, both computers, smartphone, and similar. Currently, this type of device is battery powered, but as you increase the number of functions of the sensor, you also increase energy demands. And this problem has to be solved because currently all devices are battery powered. So it becomes interesting to study how energy harvesting can support this type of devices. For example, we have several work literature that address harvesting power from tires with piezoelectric transducers. Most of them focus on lab scale validations. A few of them run on field tests, like on real tires, cars, and test machines. So normally what happens is that the tire undergoes some deformation, especially we have an extension on the point of contact with the road, and we have two compressions surrounding it. So the typical deformation we have on the angle we expect is as this shape, part of the screen. But and the idea is to place energy harvesters on the tire here. Take all this information. So the transducer is important, but of course also the circuit that converts power is important. I think it is as important as the harvester to have full efficiency. And to design the circuit, the power conversion circuit, it's important to know exactly what voltages, what currents are developed inside the tire during the real motion of the tire in real application. So in this case, this motivational work, we designed a wireless telemetry to support the design of the micro power management circuit that we were developing in a research project. So basically, we need realistic data to support the design of the power converter. So as a proof of concept, we decided to use flexible piezo transducers, and literature many work exploit PVDF transducer with their elasticity. But we know that PCT has a higher piezo coefficient. So we decided to use some commercial devices to validate the work. We decided to use some microfiber composites that are available on the market. Namely, these two devices from Smart Material. They have same width, active area 5 millimeters, and width 14 and 28 millimeters. So this one is double wide with respect to the other. The transducer on the tire work in forced displacement mode. So they're not resonating. They just absorb the deformation of the tire and follow it. And so the circuit that we can use to model the device is a current source, IP, with in parallel capacitance, which is the capacitance for the electrodes of the device. So let's go on. So this is our setup. We decided to make a full real world validation. We attach the transducer to the inner liner of the tire with some double-sided tape, 50 micron thick, with strong adhesive force. We designed a circuit which is placed on a small rubber foot which is glued on the tire. And we also had to optimize the size and direction. For example, the direction is perpendicular, is orthogonal to the motion of the tire to reduce the possible stresses during motion. Then we will see we need a high voltage, low leakage capacitor to make accurate measurements, and also a battery to power the sensor to the telemetry platform to transmit data. Both are attached on the front tire. Then we inflate the tire, we put it on a ring, we put everything on a drum test machine where we can apply axial loads up to thousands of Newton and speeds up to several tens of kilometers per hour. Yeah, we use normal car tires for the tests, and yeah, we use this platform to validate, like to acquire measurement, to understand how the transducer is working inside the tire. The method can be applied to other transducers, so it's general, so it's just a proof of concept. So this is a description of our circuit. We can make 3 types of measurements that are helpful to design circuits, like open circuit voltage, short circuit currents, and also we can extract the static power transfer characteristics. We decided to use wireless microcontroller module. We are compatible, for example, with both Arduino Nano and the ESP32 platforms. The circuit is composed of some analog readouts, which is described in the next slides. And the microcontroller drives the measurements and acquires data with its ADC as we decided to use a Wi-Fi module because it's extended range. Because when you run tests, we have a control room of the machine, which is in a separate environment for safety reasons. And then we needed like extended range and fast bandwidth to get the data. So we developed a web interface. The micro can run a web server, and we acquire data and we transfer them to the web interface to the user. So this is the first measurement. We measured first open circuit voltage, because the voltage in this type of transducer, this application can range from tens to hundreds of volts. It's very, very high voltages. But in any case, the leakage must be minimized, because any small load can affect the measurements, because voltages are high, but the power is still low. So any small current can really decrease the voltage and void the measurements. So we decided to use operational amplifiers with FET input stages. We decided to use high impedance resistive divider to minimize leakage, and solid state relays to separate the unused parts of the circuit for not affecting the measurements. So we used basically amplifying configuration, which is non-inverting summing amplifier with a reference voltages which is located half the supply voltage. And so this can scale voltage up from plus minus 160 volts down to like 0 VDD range, so that the micro can acquire correctly the devices. These are some results. We can observe that during motion, the waveform have the same shape that you would expect, that reflect the formation of the tires. So we have 3 peaks, 2 positive and 1 negative. We observed several relevant information. The main is that the amplitude is not changing much with speed. Just time scale just moves faster. The second aspect is that the width of the transducer is not affecting the voltage. This could be reasonably expected. And another aspect we observed, it's not showing the figure, is that the axial force that we apply, in this case it's 3,000 Newton applied to the tire with 3 bar pressure inside, is significantly affecting the amplitude. So the more is the axial force, the higher is the developed voltage on the devices. But still the shape is preserved. You can observe the shapes are still quite clean, and this is important information to know how to size the conversion circuit to use with the devices. Second type of measurements is about short circuit currents. We know that the measured current depend on forces, piezo materials, and similar. In these cases, we use bidirectional precise current sense amplifier with a shunt resistor. We decided to use some parallel switches to modify the measurement ranges. We can range from plus minus 3 milliamps to plus minus 80 milliamps. And we applied, of course, shunt resistor that can be considered a short circuit from the point of view of the transducer, which has really very high impedance. And we made some like measurements to understand what happens in the device. Even in this case, we have relays to isolate the section. These are the results. So we have waveforms that are compatible with being the derivative of the voltage, as you can observe. We observed in this case that the width of the transducer is really proportional to the amplitude of current. You can see that the 14 millimeters transducer on the right is basically 1/2 the amplitude of the one on the left, which is the double width devices. In this case, the currents are proportional to speed. So the higher the speed, the higher the current. And they also increase with axial force, which we have not shown here for reason of time. Yeah, we can go on. The third type of measurements is extracting static power transfer characteristics. So we applied a basic standard interface with a passive rectifier, and we applied variable loads to the transducer to understand how it behaved in terms of optimum load. So basically, we introduced a load switch. You can see it on the right, our load. The load switch is controlled by the microcontroller that can apply a specific bias voltage on the output of the rectifier and keeps the voltage of the rectified voltage in between a small range between the desired bias voltage. It activates the load to achieve this. The microcontroller can then sample the time instance where the switch open and close, the voltage, and can compute the average power that is transferred to the load. We have some also dividers to scale properly the voltage for the microcontroller. In this case, these are the results. We sampled the characteristic of several speeds for several transducer. This is just one of the results. We can observe that the power is increasing with speed, but the interesting thing is that the maximum power point is still located like at 20 volts, and the region is quite flat. So the load the converter can apply can be like quite flexible, provided we work in this region. Okay, to understand what really is happening. Then we moved on. We designed some conversion circuit to validate the behavior. We found that the platform is also compatible with this type of designs. And we observed both voltages happening on the circuit, like the charging of the capacitor with the sensor loads. And we designed also a second circuit, which is a synchronous electric extractor, more specifically the interface that extracts the power when we have peaks, and we transfer with the resonance circuit. In this case, we observe both of the charging curves of the capacitor with the load of the sensor and both the chopped waveform of it's helping design the circuit. To conclude, acquiring data in realistic condition provide pressure information for circuit design. The telemetry platform is flexible. We started from transducer, we moved to circuits, and it can apply to other sensor. The constraints are the high voltages and the low level of power involved to be measured. Also, reliability is important because tires are a very harsh environment to put electronics in. Thank you very much for your attention.